All right, we are taking a look at the third section, big section. Going to spend some time here. Want to point out right away that we're diving into something that you were doing last spring, stoichiometry. Okay, so this is some challenging stuff. So take it slow. Pause the video if you need to, and just make sure that you are really dialed in and trying to make sure you understand everything that we're doing here. Now, do want to have out that periodic table and do want to have out that calculator so that you are ready to go. So if you not have those things, grab them, and then we can get going here. So, all right, stoichiometry. So, what is stoichiometry in sort of a very basic idea? It's basically if you have one chemical and then you're trying to turn it into a different chemical. Stoichiometry is the way that we do that. So if I got chemical A and I want to turn it into chemical C, then I can't just do that. I can't just do that with things like grams. I'm going to have to go from whatever I have for A, turn it into moles, and then I can turn it into C. So we're going to do a lot of this like you have grams or you have milliliters, you have a thing, and you're going to turn it into moles so that you can then turn it into the other chemical or the other item. And so that's a lot of what we're going to do. So it says right here, great start to this because we're going to talk about these all the time. Conversion factors are your friends, and they're the things that are going to allow you to turn one chemical into another. And so when you use conversion factors, and you use coefficients, then you're doing what we call stoichiometry. So you might be like, well, what the heck is a coefficient? Well, that's just the numbers we write in front. So maybe we had 2A's and 3C's. Well, those are coefficients, all right? So that's pretty standard stuff. All right, so we're going to write some stuff in here. A, conversion factors are going to be, when we're using the conversion factors and we're using the coefficients, what we're going to be using as a big tool is what we call the mole. Remember, the mole is super important. Got kind of a wonkiness there. Let's try this again. We're going to use what's called the mole ratio, and you're going to always have this. This is the step that lets you go from chemical A to chemical B, and that's going to be critical. Now, sometimes in these IB textbooks, they're going to also use this term, a chemical equivalence. And so couple of terms for the same thing. So just kind of be aware of that. Mole ratio or chemical equivalence. And so my chemical equivalence up here, if I was looking up here, my chemical equivalence would basically be that there's 2 A's for every 3 C's. So 2 moles of A for every 3 moles of C. Right? And so that's a ratio. That's the same as a chemical equivalence. All right. So that's what we're going to be using as we move on. All right. So now we're going to dive into a problem. And this problem is a challenging problem. It is something where we're diving in and we're definitely going to be it's going to be a little bit more difficult than some of the other things that you might be used to. Now, don't worry, I'm going to give you a significant amount of practice on this because we didn't get a lot last year. But I want to show you kind of a tough problem initially, and then I'll show you some another one that's a little easier, and then I'll let you guys do some practicing. So first thing here, how many milliliters of water are produced by the combustion in abundant oxygen of 775 milliliters of octane? Assume that the volumes of both liquids are measured at 20 degrees Celsius, where densities are 0.7025 for grams per milliliter for octane and 0.9982 grams per milliliter for water. You're like, holy smokes, that's a lot. Yeah, that is a lot. This is a big problem. And so first thing we're going to do is when you have a problem like this, you're going to identify something right away. It's going to be asking for water, milliliters of water, and it's going to give us milliliters of octane. So right away, I know that this is stoichiometry because I am going from chemical A to chemical B. So right away, I know that I'm going from chemical A to chemical B. All right, so we now need to go ahead and come up with a plan, and with this plan, we have got to have the piece that's critical that we don't have is you have to start with a balanced equation. No equation, no success. All right, so you've got to have an equation. So this is back to what we've already learned. You've got to be able to take and create your equation from a sentence. So what is the key word here? Look through that. What do you think what's the big hint they gave? Read that example 10. Big hint is right here. Combustion. That is IB's favorite equation, their favorite chemical equation, their favorite reaction. They love combustion. So what you want to be able to do is you want to not be you want to be able to move past the initial sentences and be like, oh, I understand what combustion is. I can do that. So we have our fuel, which is octane, and we know it's combustion. So what you do is you write down the C8H. Oh, sorry, I'm going to give myself a little space because I want to be able to write on top of that in a minute. So let me back up. So it's going to be C8H18. And now combustion. Okay, so hopefully you either looked it up or you remember from last year, but combustion is when you take a fuel, we got our fuel, and you add oxygen, and then that fuel combusts and it's going to create carbon dioxide and water. So there are 3 pieces of every combustion problem that are identical, and those are the oxygen, the carbon dioxide, and the water. The only thing that changes is the fuel source. All right, so we're going to now have our equation, and now we're going to balance it. Okay, so I got to balance it. So first thing on balancing, I would just go ahead and do my carbons. I always do the non oxygen, non-hydrogens first. So carbon first. Then I'm going to do hydrogen. I always do oxygen last. So I've got 18, so I'm going to put a 9 here. And then I'm going to come over here and I'm going to say, okay, 2 oxygens on the left. And then I've got 16. So 8 times 2 is 16. And then 9 times 1 is 9. So 16 plus 9 is 25. Okay, so let's go over here. We need 25 on the left. So you got 25 on the right, you need 25 on the left. So what's half of 25? So I'm going to multiply it by 2, right? So what's half of 25? Half of 25 is 12.5. All right, so now what were you not allowed to do last year? Well, you're not allowed to have a 12.5. Weren't allowed to have a decimal. So there was a trick for this that I taught my kids. And the trick was that if you have a decimal, just multiply everything by 2 to get rid of that 0.5, because it's always a 0.5. It's never a different decimal. It's always 0.5. So you multiply everything by 2 to get rid of it. So if we multiply everything by 2, then that would become a 25, right? And then it would be back to a whole number. So that's what we're going to do. We're going to multiply everything by 2. So 1 times 2 is 2. And then let's go ahead and put our 25 in a better spot. So let's go ahead and put it right here. And that's a 2. And then that's 8 times 2, right? So that's going to be a 16. And then 9 times 2 is an 18. So there's our coefficients. So you might want to clean those up a little bit, but it's going to be 2, 25, 16, and 18, right? So I can kind of clean that up a little bit. I can clean this up a little bit. I'll put the 18 in there, put the 16 in there, and then we've got our 25. There we go. All right, so you've got your balanced equation, step 1, awesome. And now step 2 is I want you to write in, so step 2, I want you to write I want you to write in what you have. I want you to write what you have. And I want you to write in what you want. And I want you to do this above the chemicals. Okay, this is very important. Keeps you from making a ton of mistakes. So we're going to say, it says how many milliliters of water? So it wants water. So here's water, H2O. So I'm going to put a question mark there above it. And I'm going to put a milliliter because that's what it's asking for. So question mark and milliliter. All right. Now I'm going to come back to the other side. And it says are produced from the combustion in abundant oxygen. Well, that just means we have extra oxygen, so it's not going to matter. Abundant oxygen means we have plenty of it. Doesn't matter for the problem. Of 775 milliliters of octane. So we come over here, and above the octane, I'm going to put a 775 milliliter. All right, then it says assume the volumes of both liquids are at 20 degrees. That's not going to matter. And the densities are 0.7025 for the octane. And I'm going to have to put that down here because I've run out of space. So 0.7025, and that's a density. And then 0.9982 for the water, 0.9982. And that's also a density. Okay, now here's the thing. Two of these chemicals are not being used. And so this chemical, carbon dioxide, and this chemical, oxygen, are not being used. And so this is what I really think is important for students to do, is that they put an X above the chemical that they're not using. We're not using those two, so we should not get confused. We should never use 16. We should never use carbon dioxide. We should never use 25. And that's where those X's help you out. Now, let me tell you what happens, though. Students do not do this bookkeeping. They get lazy and they try to just do it without this, and they get confused. This is a really long, challenging problem, and so you want to do the bookkeeping, all right? So I'm